We now begin our next unit, which is on momentum. For those of you enrolled in Honors Physics AB and AP Physics C, this is Chapter 9. For those of you that are enrolled in Physics AB, this is Chapter 7. In order to begin to describe what is called momentum, we have to first of all begin to describe distributions of matter. We have not done so up until this point in the course. In order to begin to describe distributions of matter, we have to define the following term, what is called center of mass. I'm going to do so, first of all, for the easiest possible case. The easiest possible case is an arrangement of point masses that are arranged in one dimension. So let's start with an arrangement of point masses in one dimension. So for example, let's say that I have the x-axis, like so, and then arranged into a line along the x-axis, I have a couple of different point masses. Let's say that right here, for example, is an M1. And this point mass M1 has a position vector relative to the origin, which I'll draw like so, x1. Okay, here's a second point mass M2. This also has its own position vector relative to the origin, x2. And then say one more. Right here is an M3, and then this right here has its own position vector relative to the origin, x3. Now I'm drawing the masses here as having positive position vectors for simplicity on the diagram, but of course they could be negative as well. Okay, now by definition we calculate the center of mass in the following way. The position of the center of mass, first of all, is referred to as xcm. And then what we do first of all is we take the product of each mass with its position vector and then add all of those products together. So then therefore, I would have m1x1 plus m2x2 plus m3x3, and then plus any additional products that we would have for any additional masses. And then what we do is we take those sum, or that sum rather, and we then divide it by the sum of the masses. That is like so. So m1 plus m2 plus m3 and so on, once again, if I have additional masses. Now there is a way to shortcut writing out all of these terms. We do so by mathematically using a summation symbol. So then therefore, using a summation symbol, we would then write the position of the center of mass in the following way. The position of the center of mass xcm is first of all the sum of the product of each mass with its position, where the letter I here is referred to as an index. Think of it this way, it's m1x1 plus m2x2 plus m3x3 and so on. And then we divide that by the sum of the masses, which using a summation symbol is used like so. Once again, the letter I is used as an index. So think of this as m1 plus m2 plus m3 and so on. Now, for those of you that have a little bit of experience in statistics, for example, those of you that may be enrolled in AP Stats, you may actually recognize that the position of the center of mass is a specific type of average. It is what is referred to as a weighted mean. So this is an example of a weighted mean. Now, if you don't have much experience in statistics, don't worry about it. It's not important for our purposes, but the center of mass actually is an example of what is called a weighted mean. Okay, now this is how we write the position of the center of mass for a series of point masses in one dimension. Let's now just broaden that to include a second dimension. So here's a two-dimensional case. Okay, so now let me go ahead and draw the XY plane, like so. And then I have an arrangement of point masses in space. Let's say right here is an M1, here's an M2, and here's an M3. And then each one of these point masses has position vectors. I'm not going to draw the position vectors here on the diagram because it would get kind of messy if I did. But right here, for example, for M1 is a position vector R1, like so. and it has components. It has an x1 like this, and it has a y1 like this. Let me just write the components here as an ordered pair for simplicity. Similarly, for M2, it has its own position vector R2, like so, and it has components. There's an x2 here and a y2. Once again, just think of that as an ordered pair. And then right here for M3, we would then have a position vector R3. Right here would be an x3, and right here would be a y3. Like so, once again, just write it as an ordered pair. And then therefore, the position vector for the center of mass would have two components. It would have, first of all, an x component, and the x component is written exactly the same way as it is on the upper board there for a one-dimensional case. So we take, first of all, the product of each mass with its x coordinate and then add them all together, and then we divide by the sum of the masses. But then we do the same thing in the y direction as well. So then therefore, there's a y coordinate to the position of the center of mass, and this is found in the following way. We take, first of all, the sum of the product of each mass with its y coordinate, like so, and then we divide by, once again, the sum of the masses. So you end up then with an x coordinate and a y coordinate for the position of the center of mass, and then therefore you can write the position vector in the following way. So the position of the center of mass for a two-dimensional case would have, first of all, its x coordinate and its y coordinate like so, written out in unit vector notation. An equivalent way of saying the exact same thing is as follows. And this is the most general way of writing the position of the center of mass for a series of point masses, this expression here. So what we do in the numerator, first of all, is we take the product of each mass with its position vector, add it all together, and then divide by the sum of the masses. These two mathematical statements here and here are identical to each other. It's just in terms of this symbology, we're breaking it up into the x and y components. Okay, now let's immediately take a look at an example involving an arrangement of point masses in two dimensions. As you'll see, finding the position of the center of mass is trivial. Okay, let me go ahead and read the problem to you, copy it down into your notes, and there's a simple diagram that goes along with it. It says, find the center of mass of an arrangement of identical point masses that are arranged in the following manner. Okay, let me go ahead and erase all of this and then draw the diagram associated with our problem. As is always the case, copy the problem down into your notes. Okay, and then we have this arrangement of identical point masses, and there are 4 of them. Now, ultimately, what the position vector of the center of mass is going to look like, well, it depends upon how I define things. So let's just go ahead and define the following coordinate system like so, and then place the arrangement of point masses here within this coordinate system in the following way. Let's do it like this. Here, 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 and here. Like so. So let's define things like that, and then each one of these guys here is a mass m. Okay, and then we have dimensions on this diagram as well. Okay, once again, I'm just going to define things in the following way. Let's call this dimension here along the x-axis A. Let's call this right here B, and this right here, for example, B, like so. This is the same distance B over here on the left-hand side as well. So in terms of A and B then, I would have to think of the components of each position vector for all 4 of these masses. Once again, I'm just going to write these components here as ordered pairs just to keep it easy. So starting over here on the lower right-hand side with this guy right here, this guy here has an x coordinate like so to its position vector that's equal to A, and its y coordinate is 0. This guy over here would be A, B for its components. This guy over here would be A, 2B. And then lastly, this guy here on the left in terms of the x direction would be 0, and then b in the y direction, like so. And now let's just go ahead, component by component, and find the position of the center of mass. So let's first of all find xCM. Okay, so starting over here on the lower right-hand side, and then I'll kind of work my way to the left, we first of all take the product of each mass with its position vector in the x direction. So I'm going to have, first of all, m times A, and then m times A, and then m times A, And then lastly over here on the left-hand side, m times 0 for that last term. Let me just go ahead and write that here for simplicity. And then we divide by the sum of the masses, which is 4m. And now if you do the math in the numerator of the expression, you just end up with 3ma, and then divided by 4m, this just ends up being 3/4 a, like so. Okay, intuitively this makes sense. Most of the mass is over here on the right-hand side of the diagram, so then therefore we would expect the position of the center of mass in the x direction to be over here towards the right. In this case, it's 3/4 a along the x-axis. Okay, now intuitively, what would you expect to happen to the y-coordinate of the center of mass? Just look at the symmetry here of the distribution of mass that we have in this problem. Okay, let's go ahead and find the y-coordinate. So the y-coordinate then would be found in the following way. Now what you do is you take the product of each mass with its y-coordinate, add it all together, and then divide by the sum of the masses. So over here on the right-hand side, we'll have, first of all, m times 0, so let me write that in. Plus then right here, m times b. And then right here, m times 2b. And then don't forget the one over here, we have m times b. And then we divide by the sum of the masses, which is once again 4m. So then go ahead and do the math in the numerator of the expression, and when you do, you end up with 4mb. And then divide by 4m, 4m's cancel out, and we're just left with b, which is the middle of the diagram, like so, in the y direction. So then therefore we can now write out the position vector of the center of mass, RCM, in component form in the following way. It's 3/4 a I hat plus b j hat. So that's basically right here on the diagram, like so. So this right here is roughly 3/4 a, this is b in that direction, like so, and then therefore the position vector for the center of mass, RCM, would look like this. Okay, the last thing to note about this example is to note the following. Notice that the center of mass is at a location where there actually is no mass at all. This right here is empty space, but this position right here is the position of the center of mass. So finding the position of the center of mass for a system of point masses is trivial. Okay, let me conclude part 1 of these calculations involving center of mass here at this point.